Okay, hey, welcome back, everybody. Today we're going to be talking about an overview of recording systems as far as they go with analog recording technology. Now, most of us are used to or have only or always used in our lives digital recording technology, like your computer, like a tablet, or your phone, to be able to record audio as a series of ones and zeros. We're going to talk about that in another lecture, but today we're going to take a little exploration on the history, how we got here. So I'm going to jump right in. Like we've talked about many times in class, when we're talking about sound, we're talking about a fluctuation of air pressure. We're talking about changes in air pressure over time. We've talked about compression and rarefaction, frequency and amplitude, all of those things. So when you want to capture it, how do you go about that? How did we first begin to capture sound and be able to play it back? So when we use the term analog, we're talking about the waveform of the recorded signal resembles or is analogous to the waveform of the original signal. In other words, if you had a perfect sine wave originally that you were trying to capture, when we capture it, there's also going to be some noise and distortion in the process because no system for recording is perfect. So you're never going to get quite a perfect replication of the sound when we're talking about analog. You might have had this example before. If you've ever used a photocopier and photocopied an image, and then you've photocopied that photocopy, if you've ever done this, you're going to notice that every generation of photocopy gets worse if you just keep copying the existing one. So there's always going to be noise and distortion in the process of capturing something analog. But let's go back to the very beginning. Where did it come from? Well, the very first instance of recorded and played back sound was the phonograph by Thomas Edison in 1877. Now, there actually was an example of a device before that was able to record sound called the phonautograph, but we're not going to dive into that right now. This was the first device to be able to record and play back sound. So let's go ahead and see how that process came about.
The moving pictures rapidly became all the rage as the new wonder of science kicked off Hollywood and all that. The only trouble with the new moving pictures was... Now, recorded sound was already around, thanks again to Edison. You see, early in his life, he'd worked as a telegraph operator using the Morse telegraph. And he'd put together some ideas that had already been around for some time in order to make this. It's called a repeating telegraph. The Morse code signal comes in here, and as it comes in, like this, it makes that needle go up and down and make indentations on that piece of paper. When you've recorded the message, you take the bit of paper off, flip it over, put it on this turntable, so that the little indentations have now become little bumps. And when you rotate this disc, the reading head goes up and down over the bumps, and when that happens, the up and down causes on-off electrical contact, and that sends the message out down the wire. The story is that one day Edison heard this thing operating at high speed, and he noticed that it made a sort of musical sound as the reading head went over the bumps. And it hit him that that was how Bell's telephone worked. You spoke at a diaphragm, it vibrated, and you could reproduce that vibration on another diaphragm somewhere else and make speech. So Edison reckoned if he could make a diaphragm vibrate, he could make speech too. All he had to do was to make speech into bumps first. And here's how he did it. He took a diaphragm, put a needle on it, and rested the diaphragm on a strip of tin foil wound around a metal cylinder. As you turned the cylinder, it moved along. So, doing so, he shouted at the diaphragm as loudly as possible, "Mary had a little lamb, its fleece was white as snow." Then he wound the cylinder back to the start point, put the needle back in the bumpy groove he'd just made, and this time, when he rotated the cylinder, what had gone in came back out.
So you can see in this first experiment, he was able to capture an analogous signal, or analogous to the original waveform, by actually having that diaphragm move and the needle drive into the tinfoil wrapped around the cylinder. Now, ultimately, that tinfoil was replaced with wax and stronger substance over time to where it was able to drive in without necessarily deforming or losing quality every single time you played it back. But even still, wax cylinders had sound quality issues of their own. Ultimately, Emil Berliner, another inventor in 1877, released an improvement upon the phonograph called the gramophone. You might recognize it more as a record player. It introduced recording on this concept of a flat disc rather than a cylinder. The benefit of that was that now, instead of the needle having to push harder to push down into wax, and so the compression side would be blunted, whereas the rarefaction side didn't have to work as hard to come back out, the gramophone actually was driving the diaphragm sideways, making the needle scratch sideways into the flat disc. In fact, if we go to this next video here, you can have a quick example where we can see what that actually looks like. As this video clip plays here, you can see essentially an electron microscope of the stylus moving backwards and forwards, or back and forth here in this groove.
The LP is not perfectly 90 degrees to the scope or perfectly 90 degrees to the movement.
So you can literally see the waveform that gets etched in here as it was etched in on an original gramophone, and now, of course, on a record player. So as that moves back and forth, we're seeing the literal compression and rarefaction. That signal gets translated out through the electronics.
Is not perfectly 90 degrees.
It's pretty incredible. So let's go ahead and jump on from there. Early magnetic recording was attempting to replace some of the challenges with this early physical recording. If you think about it, that every time we would try to record then using something like a gramophone, it took a lot of energy to move that needle back and forth, scratching its way through a wax cylinder. So as that needle was scratching its way along during the recording process, of course, that was going to inherently lose some quality. It was not going to have as high a frequency, because the needle couldn't move back and forth as high frequency as humans could hear. You were going to have some loss in the quality. There's going to be noise in the process. So early magnetic recording was an attempt to solve a lot of these problems, as well as make the ability to do things like editing, like erasing the media, whereas with a wax cylinder or a wax disc, you couldn't really erase it. So the first working magnetic recorder was called the telegraphone, and you notice it uses some similar concepts here to what we already saw with the gramophone and the phonograph, in that this was on a cylinder, but it was using electromagnet waves to be able to rewrite magnetism over the surface of a magnetic device. So ultimately, where that ends up is magnetic tape. Magnetic tape was going to allow us to be able to play tape that is literally covered with magnetic dust, play it along underneath different types of magnets. So some magnets would be able to rearrange the magnetic dust on that tape. Others would be able to be influenced by that. So Dr. Fritz Flumer was granted a patent for the application of these magnetic powders to paper or film. So the first commercial magnetic tape recorder, the AEG Magnetophone, was the first recorder that you could buy, and then also utilize tape to be able to record, play back, and even erase that tape over time. Now, most of these technologies were invented in Germany in the early 1900s, and as they continued to develop them, being able to record and play back tape was used in a lot of propaganda in things like the World Wars, World War II, and ultimately, by the time we hit the late 1940s, just after World War II, we started to see these technologies making their way back to the United States as different American GIs brought back examples of analog tape recorders and were able to start utilizing those here in the States. So by the late 40s, we had two of these magnetophone tape decks that make their way back to the United States, and that started this revolution in the music recording process, because now we're able to not just record, but we were able to actually make edits in the recording. So you could literally cut the tape and splice different sections together. So if you think about it, prior to this, just about everything that you would hear, if it was recorded for the previous 50 years, was pretty much exactly as it happened. The quality wasn't great, but there was no good way to edit things like a wax cylinder or a wax disc. So with analog tape recorders making their way back, now all of a sudden we have people being able to innovate. So Bing Crosby, the great artist and performer, was one of the first ones to really put this to work. So Ampex, a company, produced its first tape recorder, the Model 200, and Bing Crosby utilized this to be able to record and later play back his show. So they would record the live radio show and then ultimately be able to play it back so that it was used as a tape delay so that it could be played back at other times. So it didn't always have to be live. Now you could capture the sound, and every radio performance didn't have to be live. So using this as a tape delay suddenly introduced the ability to have reruns, to have shows that were really great play back later, to edit those shows down to the best pieces. Then, Bing Crosby gave a friend, Les Paul, the great guitar player and musician, a tape machine, which he, after taking a look at, decided to modify, creating the first sound-on-sound recording. He ordered an extra record head, bolted it onto the front of this, added it to the recording process, and was able to not just record one layer of sound, but also go in and record additional layers of sound on top of the original recording. This ultimately led to recordings that had layers of sounds and guitars and instruments that nobody had ever seen or heard before. It was such a fresh and new sound. Let's go ahead and take a quick look at how that transpired into one of his most famous songs, How High the Moon.
But maybe they've got time to tell us, Les, how you really make your record. Starting at A and moving slowly on to B.
Seriously?
Seriously,
All
on
right.
the level.
We turn the tape machines on. They're just a standard, regular Ampex tape machine. And we play the first part on the guitar. This is the rhythm part. Now,
Could we hear that back?
yeah.
Just to be sure there's
Let me
no,
have some earphones.
no trickery here?
Yeah. And you can hear that on here.
Well, sounds practically the same.
Almost.
All right. Now, what do you do? Now you put your earphones on and you play another part to it. Is that
That's
right?
right. Now,
I see.
put these things on. Now, let's see. All right, I'll play the second part to this. Yeah, they're both in. All right.
I see. Now, could we hear those stages back and then you maybe ad-lib something to it live?
Like the finished product?
Yeah.
All right.
I mean,
I'll play a drum part like that.
all right.
And add that on.
Fine. All right. Say when.
When? Got it?
I get the idea now of the background. That's the background, right?
Now, how many tracks, what's the most tracks you've ever made?
Well, the most that we've put out on the market is 12 guitars and 12 of Mary singing.
Does that mean 24 tracks?
Very good.
Well, could you play that back to us and maybe put in a 25th?
Sure.
Just to earn
Well,
your-
it'll actually be 26 because Mary will sing one and I'll play one. That's to keep
26,
it
26 tracks of How High the Moon.
26
All right.
parts.
All right.
26 parts.
All right.
Recording.
Well,
Parts. Take it in.
all set.
Somewhere there's music, I'll paint the tune. Where there's heaven, high the moon. There is no moon above, love is far away too. Till it comes true that you love me, yes, I love you. Where there's music, I'll dare no fire. Where there's heaven.
So one of the things you're going to see here is obviously you can hear all the layers of instruments, all the layers of guitars, all the layers of voices. And this was something that was revolutionary at the time and blew people's mind. It sounded cool. It was a new sound. And obviously it's a pretty amazing songwriting too. It's worth taking note that the kind of overdubbing that Les Paul invented was what they called sound-on-sound overdubbing. In other words, every time he recorded a new layer, it was mixed in real time onto the existing tape. So it wasn't actually multiple tracks. They weren't separated out to where you could adjust them independently after the fact. Everything was mixed in together live and in real time. And so while it was still amazing and it created new sounds, that really pushed analog tape recorder manufacturers to start to explore new ways of being able to record multiple tracks of tape as well, so that they could record things on individual components or individual slices of the tape, so that you could now adjust them independently and edit them even independently as well over time. So let's go ahead and take a brief look at the analog tape recorder and what the main components are, so that if you're ever interacting in a studio or with a producer engineer that's been working on this for a long time, you can at least identify and speak that language. So when we talk about an analog tape recorder, let's go ahead and jump into this. The first system you're going to see is the transport. If you've ever used any old analog cassette recorders or cassette tapes, this transport is what actually plays the tape back through a series of rollers over the series of magnetic heads and then captures it up here on a take-up reel. So we've got the transport system that physically moves the tape across the heads and keeps that moving at a consistent speed. In addition, we have metering. How loud is each lane of the tape or each segment of the tape being recorded to? And in this case, you see a 24-track tape machine. And so the meters tell us just how loud each one of those tracks is being hit. And then finally, you have the electronics that are doing all of the work and the magic behind the scenes. So let's go ahead and take a quick look at how an analog tape recorder records.
Tape recording uses electromagnetic induction to convert an electrical audio signal, a voltage, into magnetism, which is then used to realign magnetic particles on a reel of recording tape, creating a magnetic representation of the audio waveform. To play back the recorded signal, the reverse is done. The magnetic signal on the tape is converted back into an electrical waveform, again a voltage, which is then sent to the audio console for mixing and processing. Multi-track tape recorders do this independently for every track. Analog recording tape contains magnetic ferric oxide particles suspended in a slurry of chemicals and binders. The audio signal, the voltage to be recorded, is sent to the tape recorder where it's routed to the record head. This is basically a temporary magnet, or in the case of a multi-track recorder, a stack of independent magnets, one for each track. The record head converts the incoming voltage for a particular track into lines of magnetic force, or magnetic flux. The tape is pulled past the record head through the magnetic flux from the head, which forms at the gap of the magnet for a track in the record head. This magnetic field realigns the particles on tape to correspond to the positive and negative swings of the audio voltage, the audio waveform, creating a magnetic version of that waveform across the length of the tape. After the tape passes through the magnetic flux from the record head, the realigned magnetic particles retain their realignment. This is the actual recording, a magnetic representation of the audio wave, which has been permanently applied to the tape. The magnetic particles consist of domains. On a blank tape, these are randomly oriented, but as the tape is magnetized by the record head, they're reoriented to follow the polarity swings of the incoming magnetic flux, the incoming audio signal. The degree to which these particles retain the new magnetic state depends on the strength of the incoming signal. Weaker signals will realign only some domains, or a correspondingly lower recorded signal level. Stronger signals will magnetize more domains. When all the domains are magnetized, the tape is saturated. Higher incoming signal levels will not be reflected in the recording signal, gently clipping or distorting it at higher audio levels. Excess tape saturation is technically a flaw, but in small amounts it can add a little analog warmth and presence to the signal, and this effect, if managed carefully, is a part of the appealing sound of analog tape. To reproduce, or play back, a magnetic recording, the magnetized tape is pulled past another head, the repro, or playback head. As the magnetized particles on tape pass this head, the magnetic flux from the tape is converted back into a varying voltage. This signal is then sent to an amplifier or mixer for playback or mixing and processing. Since the changing magnetic signal is recorded across the length of the tape, the actual length of the magnetic version of the waveform depends on the speed at which the tape is pulled past the heads. Tape speeds are measured in IPS, inches per second. For professional recordings, the standard speeds are 15 IPS and 30 IPS. Smaller or semi-pro recorders might operate at 15 or 7.5 IPS. 30 IPS provides the best high-frequency response and greatest freedom from audible dropouts, but eats up a lot of expensive open-reel tape, especially in multi-track recording, and requires more robust motors and mechanicals to handle the tape at the higher speed reliably. 15 IPS is a good alternative and offers slightly better low-end response.
So let's go through and take a look at some of the specifics of that. When we talk about the magnetic media that analog tape is, we can see that it's got a base material made of essentially some flattened PVC. We've got a back coat that controls the friction as the tape is pulled through those record heads that we looked at. The binder holds this oxide or oxidation, this iron dust essentially, and that magnetic oxide is essentially made of these domains. You heard him refer to the domains, which are essentially gajillions of tiny little magnets, little magnetic particles that are spread across this with positive and negatives. So initially, if you were to just play those back because they're not oriented in any specific direction, they're just going to play back as noise. So if you're playing back some empty tape, you're going to just hear noise. However, as it goes under that record head, the record head, which is a magnet, remagnetizes by creating that magnetic flux as the tape passes underneath. If you hit it with a stronger signal, it reorients more of those magnets. If you hit it with a weaker signal, it reorients less. And so as a result, as it does that, as the tape is played underneath and hit with those pulses that correspond to the compression and rarefaction of the waveform that was coming in, more of the magnets get recorded or get reoriented, and that's what creates that sound, that analog waveform that essentially goes across the tape. So the orientation of those magnetic domains is, in this case, we're seeing the unmagnetized versions, which are random, and then the magnetized versions, which are not random. They're aligned, and as a result, you've got signal recorded. So here we can see the analog tape recording process. The three heads that you're going to typically find on most analog tape recorders are these: the erase head, the record head, and the playback head, each of which is essentially a magnet. So when we look at this, the erase head is one that when they apply magnetism through it, it's able to erase or essentially unorient those magnets by hitting it with randomized magnetization signals. It's able to erase something. So if you need to go in and suddenly erase a track on tape, you can do that with the erase head. Of course, the record head is what takes those randomized domains, and by hitting them with strong forces of magnetic flux, it's able to reorient those domains into more specific positive and negative orientations. And finally, the playback head is how we listen to what's been recorded on the tape. The playback head is a magnet that is then influenced or able to be moved by the magnetic domains as they pass underneath it, and that creates magnetic flux that goes out, gets converted to electricity, gets amplified, and of course gets played back. So when we talk about the tape recorder, he already mentioned that there are multiple speeds that we can play that tape through. So if we're playing it through these tape heads, playing it past the tape heads, how fast does it go and what difference does that make? Well, like he mentioned, there are essentially multiple inches per second standards for analog tape. So the highest quality one would be 30 inches of tape going past the heads per second. Like he mentioned, tape recorders that could do that required more robust components because they were moving tape through really fast at 30 inches per second. But the more tape that went through, the more accurately you were able to capture high frequencies because there was more tape, there was more domains going underneath the record head, and as a result, you could hit it with higher frequencies. So ultimately, that was the greatest quality. However, it used twice as much tape as its cousin, 15 IPS, or 15 inches of tape per second. 15 inches of tape per second, or 15 IPS, obviously could not capture as high of frequencies and wasn't going to have as many domains passing underneath to accurately capture that signal. And as a result, 15 inches per second was going to be lower quality. However, it was still very popular, and it used half as much tape as 30 inches per second. And then there was a really lower quality version that you'll still sometimes see at 7.5 inches per second. 7.5 inches per second could not capture really high quality or high frequencies, but it used only a quarter of the tape of 30 inches per second, so you could make your tape last a lot longer. And if you were just recording something like speech, or you just didn't need to capture the highest quality, you could get a lot more bang for your buck. And considering that 24-track reel-to-reel tape, 24-track reel-to-reel tape still runs about $200, and a whole reel might only get you 15 minutes at 30 inches per second, 15 minutes of record time. It was very expensive to use tape, so trade-offs were often made. When we talk about the tape traveling through, essentially it's that relationship of time to the physical length of the recording tape, right? So how many inches of tape are running past that every second? So of course that also meant that you needed to play it back at the speed that it was recorded. So that constant rate of speed during playback and recording was required to make the pitch stay the same, to eliminate the what we called wow and flutter. If you've ever played back an old recording and you hear the pitch fluctuate and speed up and slow down over time, then you know what it sounds like when that tape is not moving back at a consistent speed. Let's go ahead and take a quick look at something like that. Here we're going to demonstrate some wow and flutter with actually a record player, but essentially it's just micro speeding up and slowing down of the tape. If the tape was playing past, or in this case the record was playing past, but it was speeding up and slowing down even just a little bit, you hear the fluctuations in the pitch and time of the performance of the recording. So let's hear what it sounded like before and what it sounds like with some wow and flutter as he slows it down a little bit.
This is now artificial flutter. Hear the wavering? Flutter is usually a quick fluctuation. Wow is usually once per rotation.
So there you see, that's an example of the kind of wow and flutter you can get in the analog recording process as well. If the tape is not cared for, or if the transport is playing faster or slower or anything except for a very consistent speed, or if over time the tape is stretched a little bit, and then it's going to exhibit that wow and flutter, as essentially that's changing the pace that it moves those domains past the playback head. So ultimately, how did this ability to record and edit and play back and manipulate our sound change the music recording process? Well, the beauty of it is, essentially, it's first started by extending recording time. When you were limited to how much time you could record on a physical flat disc, the only way you could have really made it a lot better was either by making smaller grooves, and we could only make needles so small and still fit all of those grooves onto a record, or we could have made the record a lot bigger. But instead, with analog recording, now we extended the recording time. Instead of recording songs that were only 3 minutes, because that's all you could fit on a cylinder or all you could fit on a small record, all of a sudden you had the ability to record a lot longer periods of time. You could change the relative timing of events that happened. You could chop out one section of tape and move it over. You could record copies of it and all of a sudden splice them together and create manipulated sound or edited sound. And then, of course, initially to add additional parts to the original performances, like we saw with Les Paul when he started adding this concept of sound on sound or overdubbing. So all of these, of course, are things that you and I think of as normal parts of the process. Nowadays, we don't have any limitations on how much time we record. Even a simple phone would allow you hundreds of hours worth of recording time just with its internal built-in memory. The concept of editing is something we take for granted because everything is done with little rectangles on a computer. Even as I'm making this video, I'm editing it in a video editing piece of software where I can see visual representations of everything. And of course, easily adding additional parts. I've already recorded this lecture in numerous different sections, starting and stopping recording, chopping pieces up, moving them around. So, and all of that started with the concept of analog tape, or started with the technology of analog tape. So this affected this modern recording process, changed it from this process of capturing a performance to creating a performance. Instead of just capturing something that was a real event that happened, now we could create something, which of course enables and facilitates all the creativity we have in the music world today. So as we're talking about these different concepts, there's a bunch of them that we have been referencing even since the beginning of this class. So when we talk about bandwidth, that's that difference between the highest and lowest frequency the device can accurately capture. We saw with analog tape that it wasn't linear. It couldn't necessarily record perfectly accurate sound. But when we talk about bandwidth, this early recording, for example, you can hear it's very limited in the frequency range. It only has mid-ranges. It doesn't have high frequencies or low frequencies. But this is an example of one of the earliest recordings that we had. So early recordings just did not have extended bandwidth. However, more modern recordings got better. So when we talk about bandwidth, we had this limited bandwidth that of limited range of frequencies. We talk about dynamic range. That continued to improve over time. As we went from recording on wax discs to recording with analog tape, all of a sudden we could record a greater difference between louds and softs. Here you notice that this early sound, in addition to limited bandwidth, it has no dynamic range. The louds and the softs are about the same. You notice when they get too soft during some of these sections, they almost get lost in the noise of the recording. As time went on, all of a sudden we had increased bandwidth and increased dynamic range, the ability to capture loud sounds and quiet sounds. Here's a little example.
A real man, what an ideal man now.
So we could suddenly record really quiet sounds like this voice, a little bit more dynamic range, a broader range of frequencies. It was a big improvement over time. Here, in this case, you can hear as time went on and we got better and better technology for recording that we also improved our signal to noise ratio, how much signal there is versus how much noise there is in a system. In these early analog recordings, you notice that there's almost as much noise as there was signal. Pretty limited, but over time, of course, that improved dramatically to where now you're hearing my voice with essentially no noise in the system. Even if you turned your speakers quite a ways up, you probably won't hear any noise captured by this modern digital system, but analog was the first step towards that. And then, of course, as we talk about other concepts like distortion, you see that each one of these improved over time. By the time we're getting to this point in, I think, the 1930s, you can hear there's minimal distortion. There's greater dynamic range. There's a greater signal to noise ratio. And then, of course, the last concept was something mentioned in the video, which is linearity. Is what goes in, what comes out. Of course, in this initial recording, you can see that in the earliest days of recording, we didn't have a linear recording process. This is not what came in. Right? If we're listening to that, we had sound where now it clearly doesn't sound like what an actual big band sounded like. So those early systems were not very linear. In other words, the sound that came in is not what came out. But over time, analog recording improved and it got more and more linear to where the sound that came in was what came out. And of course, modern digital systems have continued to improve on that. So that's a brief introduction to analog recording technology. I hope you enjoyed this. If you've got questions, be sure to bring them up in class, and we'll look forward to seeing you then.